Now we're going to look at systems of linear equations via the elimination method. If you haven't seen the first two videos in the series, then you can check those out in the links in the description to the video. So we have graphed in order to find a system of linear equations. Now we're going to turn to some algebraic methods, the first of which is the elimination method. In order to solve with the elimination method, we want to line up all of our variables and equal signs on the two equations that we have. Then we're going to force one variable to have opposite coefficients in the two equations. Then we're going to add the equations together, eliminating a variable. The variable that remains, we will solve for, and then we will find the other variable, the variable that we eliminated. In some books, this is called the addition method instead of the elimination method because of this third point here. We add the equations together to eliminate a variable. So that's our ultimate goal. Some books, because we're adding equations together, call this the addition method. Other books call this the elimination method because when you add the two equations together, you eliminate a variable. So let's take a look at an example so that we can follow the steps that we talked about. We're going to look at the system of two equations with two variables that you see on this slide. The first equation is 4x minus 5y equals 22. The second equation is 6x plus 5y equals 8. In this system, we already have the lineup that we wanted to. By lineup, I mean we've already lined up the variables and the equal signs on the equations. In the two equations, you'll notice that the x terms are right above and below each other. The y terms are also right above and below each other. The equal signs are above and below each other, and the constants are above and below each other. As long as we have those things lined up in column format, we can utilize the elimination method. So that step's done for us. Now it turns out the second step is already done for us as well. You'll see that the y terms have opposite coefficients. One is a -5 and the other is a +5. Opposite coefficients mean not just opposite signs, but also means that they add up to 0. Okay, so -3 and -8 are not, or excuse me, -3 and -3 are not opposites, those are the same. -3 and +8 are not opposites. We want opposites, meaning add to 0. Okay, so let's take a look at how to solve this system, knowing that we've already kind of done the first two bullet points, or in other words, the first two bullet points are already done for us. So here's our system of equations, which we've already have lined up. Oops. And we already have opposite coefficients on the y's. In fact, let me just write that down. Opposite coefficients on the y's. So that's already good. Since we have opposite coefficients on the y's, we're going to add the equations together. keeping the equal sign in its place. So when you add 4x plus 6x, you end up with 10x. When you add negative 5y and positive 5y, you end up with 0y, or just 0. Since I don't have to write down 0, I'll just keep 10x on the left, and I won't write the plus 0. Or I could write the plus 0 now and then eliminate it in just a second. The equal signs, we're not going to add, we're just going to drop down the equal signs. That's why it was so important to line things up. 22 and 8 add to give us 30. Now that we've added the equations together, now we can solve. In order to solve this equation, all I have to do is divide by 10 on both sides. So divide by 10 on the left-hand side. And then divide by 10 on the right-hand side. Doing that gives me an x, which is equal to 3. So I divided by 10 on both sides. Now I have x equals 3. Now this gives me the x coordinate for my solution to this system. In order to find the y coordinate, I go back up into one of those equations. And it doesn't matter which one. I'll take the second equation, although you could have just as easily done it with the first equation. And I take that second equation, I replace x with the number 3, and I solve that equation for y. Now that I know that the x coordinate is going to be 3, my y coordinate is going to be the y value that makes this equation true. So let's go ahead and solve that. 18 plus 5y equals 8. Subtracting 18 from both sides. Let me just write that, minus 18 on the left, minus 18 on the right. Good. Subtracting 18 from both sides gives me 5y is equal to negative 10. And then I divide both sides by 2. Or not by 2, I'm sorry, by 5. So divide the left-hand side by 5, divide the right-hand side by 5. That'll give me y equals negative 2. If you ever want to check that we have the right solution, then we can plug in the 3 for x and the negative 2 for y into both of those equations and see that we get a true statement. In this case, we would. I won't go through the details of that. Lastly, when you are writing a solution, if you write it as an ordered pair, the x always comes first, the y comes second, in the standard versions of ordered pairs. You always do x comma y. So in this case, we have 3 and negative 2. So that's the solution to the system of linear equations that we saw displayed above here. So that is the solution. So the only thing we need to do is figure out, well, what if we don't have opposite coefficients on one of the terms? How can I get opposite coefficients on one of the terms if I need it that way? That's what we'll do in the next example. Here is example 2. We have the system 3x plus 4y equals -4, and 2x plus 5y equals 2. Once again, the first step of the elimination method is done for us. The x's are aligned, the y's are aligned, the equal signs are aligned, and the constants are aligned. We'll see later, they don't always have to be aligned with x's and then y's and then equal signs and then constants. You can kind of align them in any way you choose, but they do have to be aligned. They do have to be all lined up in essentially the same columns. Obviously, on this one, we do not have opposite coefficients on the x's, and we do not have opposite coefficients on the y's. Opposites mean that when you add them up, they'd add to 0. If I add up 3 and 2, they add to 5. If I add up 4 and 5, they add to 9. So here's our system in a Word document. Now, because we don't have opposite coefficients on our variables, what I'm going to do is I'm going to force opposite coefficients. Maybe I should have written to begin with that these are already lined up. So the variables are already lined up. Next step, I need to force opposite coefficients on the y's. Now, I actually could have forced opposite coefficients on the x's as well. It's just as efficient to force opposite coefficients on x's as it is on y's. So if you prefer x's and I prefer y's, eliminate whichever one you like. Now, here's what we're going to do. We're going to focus. I'm choosing to force opposite coefficients on the y's. So I'm going to focus on the coefficients of those y's. The coefficients of the y's are 4 and 5. 4 is the coefficient of y in the first equation. 5 is the coefficient of y in the second equation. What I want to do is I go to each of my equations, and this is going to be a two-step process. So I'm going to take the coefficient of y from the other equation and write it out front of my equation. So I'm going to write the 5 out front of the first equation, and I'm going to write a 4 out front of the second equation. Now, what I'm getting ready to do is multiply both sides of an equation by a number. We know that's not going to change the solutions to the equations when I multiply both sides by a number. So that'll keep the solutions the same, now just with different coefficients. But before I start multiplying, I need to change the sign on either the 5 or the 4. I need to make the 5 into a -5, or I need to make the 4 into a -4. I think I will choose to make the 5 a -5. You could have just as easily made the 4 a -4. If I just keep +5 and +4 in front, then when I multiply through, I actually get the same coefficients. So by changing the sign on one of them, now when I multiply through, you'll see that in the first equation, I get -15x minus 20y equals a +20. -5 times -4 is +20. By the way, some people will probably write parentheses around the left-hand side. and parentheses around the right-hand side. I tend not to do that. I tend to just write parentheses around the entire equation. There's different ways to do it. Now, when I multiply the 4 through into the second equation, what happens is I end up with 8x plus 20y equals 8. Notice what I have for my coefficients of y's. One of them is a negative 20, the other is a positive 20. And I can do that no matter what the two equations are. Once they're lined up, I take the coefficient of y from the second equation, write it in front of the first, take the coefficient of y from the first equation, write it in front of the second, and change the sign on one of those numbers from a negative to a positive or a positive to a negative. Every time I do that, you'll get opposite coefficients on the variable, so long as you've done it right. Now we can go back to the standard elimination method, where we have to now add the equations together. When you add the equations together, negative 15x plus 8x gives you negative 7x. The minus 20y and the plus 20y add together to give you 0. The equal signs just drop down, and the constant terms add to give you 28. Divide both sides by negative 7. I don't think I'm going to show that step. I think you can figure that out on your own. We've done, or hopefully you've done that enough to understand what's going on. 28 divided by negative 7 is a negative 4, so x is equal to negative 4. Now, what happens most of the time? Most of the time, what people will do is they, at this point, will go back up, grab one of these equations. Like I said, it doesn't matter which. So just like last time I said, it doesn't matter which. And they'll try to find the y by plugging in x is negative 4. Uh-oh. Must hit the wrong number or something. So we have 2x plus 5y equals 2. Let me make sure that's black. Replace x with a negative 4, and then solve for y. 2 times negative 4 would be negative 8, plus 5y equals 2. Add 8 to both sides, you'd end up with 5y equals 10. Now divide both sides by 5, you'd get y equals 2. Again, I'm not showing every single step there, but that's the idea. And so my solution is negative 4, 2. So if you find your x, you can find the y by plugging it in to one of the original equations. And obviously I chose the second equation, but you could have just as easily chose the first equation, and you would have also ended up with y is 2. So whichever equation you choose, you'll end up with the same solution. Let's move on to another example. Here's our system, 4x plus 2y equals 2, and y equals 1/3 x minus 4. So you'll notice this is the first time that we do not have our variables, our equal signs, and our constants lined up. But we can fix that. So let's go and make sure these things are lined up and then use the elimination method. Now, in order to line the terms up, I noticed that in my first equation, I have the x come first, then the y, then the equal sign, then the constant. In my second equation, I have the y, then the equal sign, then the x, then the constant. If you want, you could make the first equation match with the second, or if you want, you can make the second equation match with the first. I think I'm going to do that. I think I'm going to make the second equation match with the first in terms of the order of the terms. So I take my second equation and I'm going to add 1/3 x to both the left and the right-hand side. So I get rid of my x term on the right-hand side, and I end up with an x term on the left-hand side. When I do that, I'm going to also make sure that the x, when I have y plus 1/3 x, I'm going to write it in order so that it aligns with this one. So we end up with 1/3 x plus y equals -4. So that's the same equation rewritten as this second equation in our system. So now what we do is we have our system, which is the two equations, 4x plus 2y equals 2, and 1/3 x plus y equals -4. Now, some people are more comfortable with fractions than others. If you're very comfortable with fractions, go ahead and use the fractions. If you're not, if you don't like that 1/3, one thing you could have done before you even messed with writing the system is you could have multiplied both sides by 3 and got rid of all fractions. So if you'd like to eliminate fractions, you could have done that. 1/3 times 3 is 1x, 1, so you get 1x plus 3y equals -12. So if you'd rather written it as 1x plus 3y equals -12, that's fine. If you're comfortable using fractions, use fractions. I think what I'm going to do, now that I see that 1x plus 3y equals -12 is the same as my second equation from the original system, I am going to use that one. So my system now has two equations, one of which is 4x plus 2y equals 2. The other is 1x plus 3y equals -12. So now things are lined up. we need to force opposite coefficients on one of the variables. Let's do it on the y this time. So we force opposite coefficients on the y's. When I do that, I take my system. I'll scroll through here. And I say, well, the coefficient of y in the first equation is 2. Let's write that in front of the second equation. The coefficient of y in the second equation is 3. So let's write that in front of the first equation. And then I need to change the sign on one of these two numbers. So we can change the sign on the 3 and make that a -3, or we could have changed the sign on the 2 to make it a -2. I'll use the -3 in this case. Now when I multiply through, I end up with -12x minus 6y equals -6. And 2x plus 6y equals -24. Adding these two together, let me write that down, add two equations together. We end up with -10x plus 0 is equal to -30. Divide both sides by -10. What you'll see, let me go to the next page here, is that x has to be 3. Once we find x is 3, the most common way of solving is plug in that x of 3 to find the y. So let's choose one of these. Let's choose the 1x plus 3y equals -12. Or if you wanted to, you could go all the way back up to here. In fact, I think this one's going to be a little bit easier to deal with. So I'll use this very first equation, y equals -1/3 x minus 4, meaning the equation that we started with in the system. So I plug in 3 to that. And what you see, hopefully, when you take -1/3 times 3 minus 4, you get a y of -5. If you have any doubt about your solution, you can always check it. But this means my solution is 3, -5. Again, always throw in the x value first. So 3, -5. You can check that if you want by plugging in 3, -5 into the first equation and 3, -5 into the second equation and checking whether or not that is true, whether both are true. Again, I will spare the time and just say it is true in this case. 3, -5 is the correct solution. Let's take a look at another system. This one says y equals 1/2 x plus 4 and y equals -3x plus 1. Now, you might think that you have to readjust these so that the x's are on the left, but it turns out you actually don't. Notice that the y's are aligned, the x's are aligned, the constants are aligned, and the equal signs are aligned. Therefore, I actually already have the terms all aligned that I need to. So it's okay that all the x's are on the right-hand side. That's perfectly fine. Everything is lined up, so if I want, I can go eliminate a variable. And that's what we're going to start out doing. So the two equations are already aligned. So now we're going to force opposite coefficients. Let's force opposite coefficients on the y's. Just because I don't want to have to deal with this fraction I want to deal with that fraction as little as possible. Okay. So let's force opposite coefficients on the y's. You'll notice that the coefficient of y in the first equation is 1, and the coefficient of y in the second equation is also 1. It's an implied 1. There's nothing in front, so it's 1, 1. So I take the coefficient in the first equation, write it in front of the second equation. Coefficient in the second equation, write it in front of the first equation. And then I change the sign on one of them. Doesn't matter which one I turn into a -1, but I'll choose this one. So -1 is going to be multiplied by that first equation, and +1 is going to be multiplied by the second equation. By the way, if you don't like this 1/2, you could have done the trick we used in the previous slide and multiplied everything by a 2 as well, and you would have eliminated that denominator. As it stands, what I'm doing, when you multiply -1 times the first equation, you get -1y is equal to -1/2 x minus 4. And when you multiply 1, that is a +1, by the second equation, you get y equals -3x plus 1. So now we have opposite coefficients. We add the equations together. That will give you 0 is equal to -1/2 plus a -3 is -3.5, or I'm going to write it as -7/2 because that's an improper fraction, and improper fractions tend to be easier to deal with. Okay. So we end up with this. 0 is equal to -7/2 x minus 3. I would add 3 to both sides. And then I would divide both sides by a -7/2. Now, when you do that, make sure when you type things in on your calculator, if you just type in divide by 7/2, it might not do the appropriate order of operations. So when you're dividing by -7/2, you want to make sure parentheses are around your -7/2 on your calculator. So take 3 and divide by -7/2, and you get some really ugly number, -0.85714 in decimal version, which if you convert that to a fraction using your calculator, you end up getting a -6/7, which is equal to x. That's perfectly fine. It's a number. Obviously, it's not a whole number. It's not an integer, but it's a rational number. And we can go back up to our equation, one of them, doesn't matter which one, either the first or second equation, and we can plug in that -6/7 to find what the corresponding value of y is. I'm doing this all on my calculator. So y is going to be equal to -3 times -6/7 plus 1, which gives me about 3.57 as a fraction. And again, I tend to like the improper fractions, so I tend to write my fractions as improper fractions. That's 25/7 as my y value. That means my solution is going to be the point -6/7, comma, 25/7. And there you go. On trying to do this equation, or trying to do this problem via graphing would be extremely difficult, because this would be a really hard point to recognize on a graph. So having this algebraic technique is a very, very nice thing. If you're ever in doubt whether or not that's a point that works, just plug it in to both the first equation and the second equation to see if you got the question right. So sure enough, when you plug in the point into the first equation, you get a true statement. So we know the point works in the first equation. If you plug in the point into the second equation, you get a true statement. So you know the point works in the second equation. So this is the solution. Obviously, this shows you solutions don't always have to have integer answers. In the next example, we have this system. X plus 2y equals 12, and 6x equals -3, 6y equals -3x plus 10. Obviously, my x's and y's and equal signs are not aligned, so we're going to start with aligning those, and then we'll get opposite coefficients and so on and so forth. All right. So let's align the terms. Now, the easy way to align the terms is to add 3x to both sides of the second equation. If I do that, my first equation is going to be the exact same thing. But if I add 3x to the second equation, on the left-hand side, I'll get 3x plus 6y. And on the right-hand side, if I add 3x, that will eliminate the 3x on the right-hand side. So I end up with a pair of equations that are x plus 2y equals 12 and 3x plus 6y equals 10. Let's force opposite coefficients. I've been forcing opposite coefficients on y's. You can force opposite coefficients on x, but I will stay with the y's for this one. So I look at the coefficient of y in the first equation, that's a 2. I'm going to write it in front of the second equation. I look at the coefficient of y in the second equation, that's a 6. I write it in front of the first equation. In order to get opposites, I need to change one of the signs. I can either change that 6 to a -6 or the 2 to a -2. I'll choose the 2, changing to a -2. When we multiply through, we end up with 6x plus 12y equals 72. And in the second equation, we end up with minus 6x minus 12y equals -20. Now we have opposite coefficients on the y's, so we need to add the equations together. When I add these two equations together, obviously the y's cancel each other out. That's how we designed it. But also you'll notice that the x's cancel each other out too. So on the left-hand side, all of our variables go away. And on the right-hand side, I end up with 52. Now, this is obviously incorrect, right? This is obviously a false statement. And what this means in terms of the outcome here is that there is no way we can find a point, plug it in here, and plug it in here to make both of those equations true at the same time. So a false statement means that the system has no solution. And that is our answer, that this system has no solution. So that if I said, what is the solution? Is the fact that this has no solution. So the system has no solution. By the way, if we would have ended up with some other number, let's say, just for instance, instead of this being a 10, what if this were a 36? Then we would have ended up getting 0 equals 0 for our answer. In that case, that would have been a true statement. And if the variables drop out and you get a true statement, that means the system has infinitely many solutions. Hopefully you remember back from our previous graphing of solutions to systems that no solutions means that we have parallel lines. Infinitely many solutions means that the lines are exactly the same. So I'm going to go back and change this to the original so that it doesn't throw things off. But false statement means no solution. A statement that's always true means infinitely many solutions. So that can happen when we start getting opposite coefficients and both terms drop out in our adding stage. All right, let's do one more example. This will be our last example, but I'm going to show you how to solve for y's and x's in a slightly different way than we have so far. And sometimes people prefer this way as opposed to the other. All right. So as you can clearly see, the x's, the y's, the equal signs, and the constants are already aligned. So that means we need to force opposite coefficients. I'll once again do the y's, even though, like I said, you could have done the x's first too. So I look at the coefficient of y in my first equation, that's a -8, and I put it in front of my second equation. I look at the coefficient of y from my second equation, and I put it in front of my first equation. I need to change the sign on one of these. Now, if I ever have a negative, I kind of like changing the negative back to a positive because for me, it's more natural to multiply by a positive. I don't have to worry about sign changes. So I'm going to take that -8 and change that to a +8 with my sign change. That's going to give the first or that's going to transform the first equation into 20x minus 40y equals 20. The second equation will transform into 24x plus 40y equals 8 times 36, which is 288. Now we can add the equations together. When I add the two equations together, I end up with 44x is equal to 308. Divide both sides by 44. If I divide both sides by 44, the left-hand side becomes x. 308 divided by 44 is 7. So x is equal to 7. Now, at this stage, it is perfectly reasonable to say, let's just plug in 7 into my first equation and find y, or plug in 7 into the second equation and find y. However, once you get really good at elimination, especially if our answers are kind of ugly, this one's not very ugly, but a couple of examples ago, we saw 6 7s or -6 7s. That was kind of ugly. If we have ugly answer, or if you don't trust yourself to plug in, what you can do is you can simply, so we found x. What we can do now to find y is simply do elimination on the x's. So if we want to do elimination on the x's, we can force opposite coefficients on the x's. you see that the coefficient of the second equation is a 3 on x. So let's write that in front of the first equation. And the coefficient on x of the first equation is a 4. So we're going to write that in front of the second equation. We need to change the sign on one of these. I'll change this 4 to a -4. And now I'm ready to multiply through. Once I multiply through, the first equation transforms into 12x minus 24y equals 12. My second equation transforms into -12x minus 20y is equal to -4 times 36, which is -144. Add these equations together. You'll end up with -44y is equal to -132. Divide both sides by a -44, and you end up with a y which is equal to 3. So I used elimination on the y's, that gave me x. Now I used elimination on the x's, that gave me y. So now I know my solution is the ordered pair 7, 3. 7 was the x. I got that by eliminating the y's. 3 was the y. I got that by eliminating the x. So 7, 3 is the solution. So you can do elimination on either variable or do elimination on both variables if you want. And as always, you can always check if 7, 3 is the solution by plugging it in to both equations and seeing that both equations give you a true statement. So there we go. And they do in this case. I should have said that. So they do in this case. So 7, 3 is the solution to the system. So now we've solved about 6 different, we have solved 6 different elimination problems. And at every single one we've done, we've taken up these steps. We've lined up the variables and the equal signs on the 2 equations. We force one variable to have opposite coefficients in the 2 equations. Once we have opposite coefficients on one of the variables, we add the equations together. That eliminates a variable. We solve for the remaining variable, and then we find the other variable. And we just saw that finding the other variable may mean that we do another elimination method on the other variable, right? So that's the elimination method. Once again, I generally call this the elimination method. Some books may call this the addition method. In our next slide, we'll see, or in our next video, you'll see the substitution method as well, and you can click on the link below to see that.